Hello, welcome in the 18th lecture of two-phase flow and heat transfer. Here today we will be discussing about condensation heat transfer. So, let us see at the end of this lecture we will be understanding basic difference between dropwise and film condensation. We will be predicting the heat transfer coefficient in dropwise condensation. We will be discussing elaborately the mechanisms of droplet interactions during dropwise condensation. We will be finding out velocity and temperature profile when film condensation is happening over a vertical surface. We will be also seeing how to evaluate condensate rate and the profile of the film over the vertical surface. So, let us start with the definition of condensation. So, condensation is one mode of heat transfer in which actually over the surface we will find out due to heat transfer gas will be converting into liquid. So, here you will find out the surface will be actually having lower temperature than the saturation temperature. Now, if we try to classify broadly this condensation, we will be finding out two modes are there. One is called film wise condensation, another one is called drop wise condensation. So, first let us try to understand what is film condensation. So, in film condensation, majority of this type of film condensation we see over vertical surface. So, here I have given you one schematic of the vertical surface. So, let us say this is the surface whose temperature is lower than the saturation temperature of a given pressure. Now, as this temperature surface temperature Ts is less than T saturation, then you will be finding out that a liquid film is being formed due to the condensation. Condensation means it will be forming vapor, it will be forming liquid from vapor. So, you will find out that this liquid is forming a film over this vertical surface. So, in case of film condensation, you will find out that entire surface is actually covered by condensate. It is not like that locally the surface is covered by the liquid, it is entirely covered, which flows continuously from the surface and provides a resistance to the heat transfer between the vapor and the surface, because this film will be acting as some sort of resistance between the vapor to come in contact with the cold surface. So, you will be finding out this is giving some sort of resistance. So, this thermal resistance is reduced through the use of short vertical surfaces and horizontal cylinders. If you want to remove this film boiling, so what we need to do on the surface, we need to give some sort of horizontal cylinders as some sort of appendage, so that the film will be breaking down, and you can once again go back to your dropwise condensation mode where gas can come direct contact with your surface. And this type of film boiling you can see in the surfaces where you will be finding out surface is clean and you are having no contamination. Then let us see the another version. So, dropwise condensation. So, you see in dropwise here I have given you one figure. In dropwise condensation you can find out over the surface we are having lots of droplets of liquid being formed. Now, this dropwise condensation majority of the time you will be finding out over a horizontal surface. But here I have given you one example just to give you some sort of comparison between the previous one and this one, that we are having a vertical surface once again, and you can find out lots of droplets are actually being formed due to condensation. So, gas is converting into liquid. Now, in this type of dropwise condensation, you will be finding out that surface is covered by drops, and the size of drop will be ranging from a wide variety. So, it will be starting from few micrometer, and agglomeration of these drops will be making you making these drops visible even with naked eyes. Here I have shown you one typical example. Now, this thermal resistance is greatly reduced due to this absence of continuous film, whatever we have seen in the previous case, in case of film condensation, and surface coating you can apply to inhibit wetting and stimulate dropwise condensation. If the surface is having very poor wetting condition, that means it is asking the drop to squeeze on the surface, then you will be finding out that dropwise condensation is being preferred. Now, let us see that how in case of dropwise condensation heat transfer can be calculated. So, here I have shown you a situation where condensation, dropwise condensation is being predicted for steam over copper surface. So, that can be written as Q equals to heat transfer coefficient for dropwise condensation HDC multiplied by A into Tsat minus Ts. Okay. Now, this HDC is very important, heat transfer coefficient in dropwise condensation. It depends on the surface temperature. So, if saturation temperature is in between 22 degree centigrade to 100 degree centigrade, we can write down the coefficient as 51,100 plus 2044 into Tsat, and if the saturation temperature is higher than 100 degree, then you can write down that is actually 255500, a constant value. Okay. So, once you know the heat transfer coefficient, once again you can go back to this equation to get the dropwise condensation heat flux. Okay. Next, let us see that how these droplets in dropwise condensation will be behaving over the surface. So, different stages of droplet evolution. So, you will be finding out at the beginning the droplets will be nucleating on the surface. At this time the droplet will be having very smaller size in the range of microns, and then you will be finding out the initially those droplets will be growing in size due to more and more condensation around that. So, it is actually increasing its size due to the condensation farther at that site. Okay. And then after some time you will find out whenever this droplet size will be becoming considerable, you will be finding out that two droplets side by side which are staying side by side, they are actually merging or coalescing amongst themselves. Okay. So, you will be finding out coalescence happens like this. Okay. Here you see the coalescence happens and the drop gets bigger and bigger in size once again. So, bigger size droplets you can find out. Okay. But at the same time, if it is on vertical surface, then you will be finding out with the increase of size the droplet is also facing the gravitational pull. So, you can find out at some time the droplet is also being dislodged from the surface. Okay. So, you will be finding out at some point of time when it is increasing in size, some droplet can also dislodge from the surface. Okay. So, loss of drop due to gravity is also very important. Apart from that, simultaneously you will be finding out over the surface smaller nucleations are still continuing. Okay. So, those are different stages of droplet evaluation, and you will be finding out if you continue in this side further, then once upon a time you will be finding out that all those droplets are actually forming a film over the surface and it is turning to film-wise condensation. Okay. Next, let us see the next subsection, which already I have told as film-wise condensation. So, let us try to see that how film boiling is distinguished from the dropwise condensation. So, here I have shown you that vertical surface over which the film is being formed. This is your liquid film being formed due to your condensation. So, here in the periphery you are having vapor which is supposed to come in contact with the surface and form film. Okay. So, this vapor I have considered as V and liquid I have considered as L. So, now first if you try to find out the temperature pattern and velocity pattern over this surface, then let us try to see what happens to the temperature. All we know that the vapor temperature will be at higher side, and obviously surface temperature will be at the lower side, which is necessary for condensation. So, you will be finding out the temperature will be a smooth fall from the vapor side to the solid surface, where it will be attaining the Ts, which is nothing but surface temperature, and here it will be attaining Tv, which is the Tv infinity you can say, which is the free steam vapor temperature. Okay. Now, at the interface you can find out that there is continuous nature of the temperature also. Okay. Now, if you think about the velocity, so obviously at the wall you will be finding out there is no slip condition, so there is no velocity over here. Obviously, on the other hand you will be having no velocity when at the bulk of the gas also. So, here you see once again the velocity is 0. So, in between whatever film has been formed, that will be going in the downward direction. So, you can find out a downward velocity in the film. Okay. And at the interface you will be finding out due to inertia you will will be finding out the liquid which is falling down will be carrying some amount of gas also along with that in the downward direction, and the velocity continuation is there. So, there is no discontinuity of the velocity. So, you will be finding out something like this for the velocity profile. Interestingly, the highest velocity you can find out somewhere inside the liquid film domain. Okay. So, let us now try to understand that how this condensate rate can be predicted, okay, m dot can be predicted, as well as how this film nature, okay, delta or film thickness nature, okay, delta is the film thickness. So, how this film thickness varies with respect to your plate. Okay. So, in order to do so, we will be doing some sort of mathematical calculation for the vapor as well as the liquid. Let us start with the vapor side. So, what we will be doing at the leading edge, that means where the film starts at this point, let us call that one as x equals to 0, where x varies in this side. Okay, that means along the plate the x varies, and y is actually the perpendicular direction of the wall. So, at x equals to 0, you can find out pressure will be equivalent to your vapor pressure. Okay. So, here we are having no liquid, so obviously the pressure will be equivalent to your PVO. Okay. Next, in this position, as we are not having any film, liquid film, so obviously the velocities will be also 0. So, we can write down that UV, VV and WV all are equals to 0. Okay. And the temperature at this zone obviously will be the equivalent to your infinite temperature or bulk temperature. So, we can call TV is equals to T infinity. Right. So, if you try to write down the momentum equation for the vapor now, as we are having all the u's equals to 0, so we will be finding out only the pressure term and the buoyancy term remains. So, we can write down del PV del x equals to rho v into g. Okay. So, once we integrate this one, we find out that PV is equals to PV naught plus rho v into Gx. Here we have used the integration criteria as x equals to 0, P equals to PV. So, boundary condition is at x equals to 0, P equals to PV naught. So, if we take PV naught common from here, we get 1 plus rho v Gx by PV naught. Interestingly, you see over here rho v is there, so which is a very small value in case of at least for the water. So, what we can do, we can neglect this term. So, we can write down vapor pressure will be more or less equivalent at this zone we can write down the vapor pressure is more or less equivalent to your PV naught. Okay. So, we can write down your corresponding saturation pressure, saturation temperature Tsat, which is actually your saturation temperature corresponding to PV, that is once again equivalent to your Tsat at PV naught, because PV is equals to PV naught we have just now found out. Okay. So, and the limiting conditions for considering this rho v very small, we can write down Tsat is equals to Tsat PV naught. Okay. Next, let us try to see from the liquid side, but before going to the liquid side, let us see the interface. Okay. So, here we are having the interface between the liquid film and the vapor. So, what we have taken a small sector across the interface. So, this is a small sector, you see L and G. Okay. Liquid is there in this side in the film and gas is there in the bulk. Okay. So, if we try to first find out the mass flow rate, okay. So, mass flow rate for the liquid film. So, mass flow rate m dot can be written as rho a Vn. Here this Vn is the actually normal directional velocity of the interface. So, here if we find out a normal of this one, so that directional velocity will be coming into picture over here. Okay. So, this is actually equivalent to L and this is actually for the vapor. So, because these two will be same, because we know that whatever amount of mass will be being lost from the gas, that will be accumulated in the liquid side. Okay. So, after doing the mass balance, let us go for the energy balance side. So, if we go for the energy balance in this across this interface, then we can write down for the liquid side m dot into HL plus VL square by 2. So, this HL is nothing but your enthalpy for the liquid side, VL is nothing but the velocity for the liquid. Okay. So, here we have added the kinetic energy portion over here. Okay. And on the other hand side for the vapor, we can write down m dot into HV, which is the enthalpy for the vapor, plus Vv square by 2. Along with that you will be having the heat transfer and work done also as per the first law of thermodynamics. So, we are having Q dot minus W dot, but obviously in this case we are not having any W dot, so we can make it 0. Okay, this can be cancelled out and easily this Q can be written as now this Q will be the heat transfer. Now, the heat transfer will be dependent on the conduction through the liquid and conduction through the gas. Okay. So, conduction through the liquid, if you write down, then that will be minus K del T del N A. Now, this N is once again the normal direction, okay, and all the properties I will be taking for L, that means liquid. So, that means this will be KL, okay, and here for the vapor side we will be getting KV into del T del V del T del N of A, right. Now, you see they are opposite in sign because one will be actually accepting heat, another one will be actually dumping heat. Okay. So, Q we can write down as the summation of both the conduction heats in liquid and vapor side. Okay. Now, if we put back this Q and W in this equation, then ultimately we will be getting a equation like this. Here I have also put the value of m dot from the continuity equation. So, I have written rho A V n dot. So, this is V n cap is nothing but actually your normal directional velocity, what I have written in place of this V n, okay, multiplied by Hf plus VL square by 2 equals to once again this is for the gaseous side mass flow rate. Remember what we have done over here, as this L and V are for the liquid side and vapor side, in the limiting condition we can write down that is on the interface. So, here both this L and V we have written as INT, this symbolizes the mass transfer across the liquid. Okay. So, this will be for the gaseous side, mass transfer from the gaseous side multiplied by Hg plus Vg square by 2, and on the other hand side we are having over here the conduction part. Now, see, in the conduction part also, as I have shown you, this conduction is actually summation of two conductions, so liquid side and vapor side, but we know for the vapor side the thermal conduction conductivity will be very low compared to the liquid side. So, this term actually we can cancel out, and this Q can be written as minus K del T del N A for the liquid side only. So, that term we have kept over here as Q, right. So, if we see this equation, so and take this first term in the right hand side to the left hand side, so I can write down that will be coming as Hf minus Hg. Okay. Why? Because this is the limiting condition at the interface, and at the interface already we have shown that there is no discontinuity of the velocity. So, you will be finding out VL will be equivalent to your Vg. So, that part will be cancelling out and you will be having Hf minus Hg, which is nothing but Hfg. Okay. So, we get in this side the conduction, and here in this side we get the your condensation heat transfer, okay, involved with Hfg. Okay, next let us see after this one interfacial condition, let us see what happens for the liquid side. So, we have taken falling liquid film assumptions. So, in falling liquid film assumptions we have written down over here the continuity x momentum and y momentum equations respectively. Okay, so, these are coming from your fluid mechanics, already you know, and here as we have already shown that del P del X for the vapor side will be rho V into G, that also we will be using into consideration, because this we have already shown for the gaseous phase momentum equation side. And energy equation in the liquid if you write down, so in the left hand side we are having convection and the right hand side we are having conduction. Okay. Next, to reduce this number of equations, you see over here we are having at least 1, 2, 3, 4 equations. So, these 4 equations, if we try to now reduce the number of dependents, then what we will be doing, we have to take some approximations. So, first approximation what we take is called Nusselts analysis. So, Nusselt he has proposed this one. What he has considered, the assumptions are laminar flow in the liquid. He has considered flow of liquid is steady, he has considered the liquid is having constant property, negligible streamwise diffusion of momentum. So, negligible streamwise diffusion of momentum means in your equation del square u del x square will be equals to 0, because x is the stream direction. So, that portion is 0, okay, diffusion, streamwise diffusion is 0. Similarly, negligible streamwise diffusion of heat. So, your energy equation, in your energy equation you will be finding out this del square T del x square will be also going to 0, okay, and negligible inertia and convection terms. So, this is very important. So, convection and inertia if you neglect, so all these left hand side and in the energy x momentum equation and energy equation will be cancelling to 0, okay. So, our equation, sets of equation becomes very simple. So, this comes from the x momentum equation, 0 already we have cancelled this inertia. So, 0 equals to rho minus rho v into g. Where from this rho minus rho v is coming? Actually you see you are having del p del x over here. So, del p del x equals to rho v into g we have got over here. So, if we put this from this equation over here, del p del x value we will be getting rho minus rho v into g. So, that term will be coming over here, rho minus rho v into g, plus only the crosswise moment diffusion is term is remaining in the momentum equation. And from the energy equation we get very simplified form del square T del y square equals to 0, because streamwise diffusion, streamwise diffusion in the energy equation and your convection has been neglected as per the Nusselt analysis. Okay, let us see the boundary conditions now. So, at y equals to 0, that means on the surface obviously the velocity will be 0 and the temperature will be Tw, which is the wall temperature, or you can call it that one as surface temperature Ts. Okay. Now, at interface, which is nothing but y equals to delta, we will be finding out that there is no gradient of velocity, because velocity is continuous over that. So, del u del y is equals to 0, as well as we find out that there the phase change is happening. So, the temperature will be actually equivalent to your saturation temperature. So, T is equals to T sat. So, if we now integrate your momentum equation and energy equation, which already we have discussed based on the Nusselts analysis, if we integrate along with these boundary conditions, then we will be finding out u from the integration of momentum equation comes out to be minus rho v g into g divided by mu into y square by 2 minus of delta into y. Very simplified integration we are having, and we have to put the boundary conditions as y equals to 0, u equals to 0, y equals to delta, del u del y equals to 0. Okay. So, we get the liquid film velocity in this fashion, and energy equation is very simple. So, 2 times integration if we do for this equation, and along with the boundary condition y equals to 0, t equals to Tw, y equals to delta, t equals to T sat, we get straightforward solution for the temperature profile. T sat minus T by T sat minus Tw is equals to 1 minus y by delta. Okay. So, you see this nature, if you see already we have shown you over here. So, this y versus u, that is a parabolic nature. So, this is the parabolic nature, and for t versus y, that is actually a linear nature. So, you see that is a linear nature over here we have seen. Okay. Next, let us try to find out that how condensate rate can be achieved. So, here I have shown you that condensate rate m dot is equals to 0 to delta rho u dy. Okay. Already we have found out what is y. So, let us put that y over here, or y I have shown you in the u I have shown you in the previous slide, liquid film velocity. So, let us put this expression over there in the integration. So, if I put this over here and perform the integration, then I get m dot is equals to, with the obviously with the limits 0 to delta, because film condensation will be in the film thickness only, inside the film thickness only. So, m dot becomes rho into rho minus rho v into g delta cube by 3 by mu. Okay. So, this is the condensate rate, very important term for condensation. And if we try to find out the mass balance, energy balance across the liquid film, then I will be writing down d m dot hfg is equals to k into dt dn into dA. If you remember this, we have already explained across the interface earlier. We have got that d m dot into hfg d m dot, this was d m dot actually, d m dot into HFG was actually k into del T del N at the interface. Okay. So, same equation we are using over here, d m dot HFG equals to k into del T del N into dA. Okay. Now, here interestingly if you see here dA is actually dx. So, this is the area. So, this rectangle if you see this rectangle is actually giving you the heat flux to the film. So, you will be finding out that dA is actually dx into 1. We have considered unitary directions in this way, in this side, okay, z direction. So, you can write down dA equals to dx. So, if I put this del T del N over here, del T del N will be once again the normal direction is y direction, already I have showed you. So, del T del N will be del T del y, and that can be reduced to T sat minus T w by delta. Okay. So, if we put all these things over here, del T del N will be delta T by d and dA is equals to delta x, we will be getting dm dot dx equals to rho into rho minus rho v into g by mu delta square del delta del x. Okay. So, what we can do once again, m we have got over here. So, if I make the derivative of m and put it over here in this equation, then I will be getting this equation. You see in this equation, in the left hand side we are having derivative of x, and in the right hand side we are having derivative of delta. So, we can easily integrate this one. Okay. So, if we integrate, then we find out, if we integrate from 0 to x, okay, then we will be finding out that this is becoming delta 4 to the power 4, and in the right hand side we are having mu k delta t divided by rho into rho minus rho v g into HFG into x plus a. Okay. Now, we need the boundary condition for finding out a. So, we need the boundary condition means we know that x equals to 0, delta equals to 0 at the leading edge. So, we get that value of a equals to 0. Okay. So, finally, the delta turns out to be 4 mu k delta t by rho into rho minus rho v g HFG into x to the power 1 by 4. Okay. So, if you rearrange now this term little bit, then you will be finding out this will be coming out as ratio between two non-dimensional numbers. One is called Jacob number, another one is called Rayleigh number, and we define the film Rayleigh number as Rayleigh number by Jacob number. Then we can get this delta by x will be coming out to be 4 by Rayleigh number, film Rayleigh number to the power 1 by 4. So, this is very important relationship. If I can find out the film Rayleigh number, then easily the delta by x can be obtained. Okay. So, to summarize this lecture, what we have done, we have described the basic differences between dropwise and filmwise condensations, and where those occurs, those things we have discussed. We have discussed the mechanisms of droplet growth and reduction, okay, in case of dropwise condensation. We predicted the film accumulation rate, okay, in case of film-wise condensation over vertical surface, and we have balanced mass, momentum and energy equation to find out the film profile over a vertical surface. Okay. So, let us test your understanding. So, we are having once again 3 questions over here. First question, necessary condition for condensation, we are having 4 answers. Part A, Tw less than Tsat, part B, Tw greater than Tsat, part C, Tw is equals to 0 Kelvin, and part D, Tw is equals to triple point. Okay. So, answer I think all of we know, answer will be part A, where surface temperature requires to be lesser than your saturation temperature. Okay. Second question goes like this, necessary assumption for Nusselt analysis. We have given you the assumptions today. So, the assumptions answers we are having as first assumption can be laminar, second assumption is neglect inertia and convection, third assumption neglect buoyancy, and fourth assumption neglect crosswise diffusion of momentum. Okay. So, the correct answer will be obviously part A and part B, because we neglect the streamwise diffusion and we will not be neglecting buoyancy, otherwise G will not be coming into picture. Okay. Let us see the last question. Condensate rate is proportional to, very simple, in the previous slide I have shown you. So, condensate rate m dot will be proportional to 4 answers we are having, 1 by delta, delta square, delta is the film thickness here, and part C is delta and part D is delta cube. So, the correct answer is delta cube in the last slide we have seen. So, with this we will be ending this lecture. Thank you.